One moment. This is the cold room. Yeah, he's feeding everyone.
And they measure the difference in the feed because if there's a gravitational wave passing the areas at that moment, slow down.
Okay, I think we're on time today. First of all, thank you all of you for participating. Looks like a good crowd today. And this is our second semester. We're continuing on this FSI Seminar Series. And then for this semester, we are really showcasing the regional diversity in space research. We have speakers from UCF, UF, and Kennedy Space Centers for this semesters. And for today, we have Joris Verbiest. He's a new faculty here at FSI, and he is an International Pulsar Timing Array Project Manager. To speak a little bit more about our speaker today, he had his aerospace engineering from the Netherlands in 2003, master's in 2005, and PhD in 2009 in radio astronomy. And then after that, he was a postdoctoral researcher from 9 to 13. He was also a Marie Curie Fellow at Max Planck Institute. And then after 2013, he's been a professor, assistant professor, and associate professor at Belfield University in astrophysics. Okay, please, the time is yours. And then for today, he'll be talking about the pulsar timing, gravitational wave detections, and much more. The time is yours. Thank you.
All right, welcome everyone, and I'm happy to see that we probably have more people in the room than online actually. So that's great. Makes me nostalgic almost. At the same time, there's bad news because it's been a long time since I gave a talk like this, especially with a live audience, which probably means that I'll go way over time. I'll try to keep a lid on that, I promise. But feel free to run out if it really gets too bad. As Dark already said, I'll talk about pulsar timing, gravitational waves, and lots of other things. I'm a bit of an odd one out at the FSI in the sense that everything I do is in the radio regime. So, I mean, literally everything is in the radio regime. And everything I do involves pulsars. Yes?
Sorry, are you welcoming comments and questions while you're talking?
Yeah, go ahead.
All right, so I just want to say we've been operating the Arecibo telescope for the past, 5 years.
I know.
So if you may want to not feel that to be the odd one out with your,
No, but I'm getting to that because
okay.
because what I'll talk about mostly is pulsars, because that's what I do. I observe pulsars and I use pulsars as tools to study other things. And I don't know if anyone here works on pulsars. You do? That's great. We need to talk. But so mostly that's what I do. The thing is, though, I don't know anything about pulsars. I don't understand them. You'll see that soon. I don't know how they work or why they do, and honestly, I don't care. Because I'm not really interested in pulsars themselves. What I'm interested in is in using these things to study other things, and that's where this much more comes from. Now, I know that the hot science, the thing that everyone wants to hear from me is that we detected gravitational waves. I'm not going to tell you that we have, because I'm not allowed to yet, and for other reasons. But I will tell you where we stand with that, because that's the thing that everyone's watching right now. So that's what most of the talk is on. All the other stuff, which I hope will lead to some connections and maybe collaborations across the Institute, I'll simply flash it up at the end, depending on how fast we go. I'll say more or less about that. Otherwise, you can see the headline and then you can talk to me afterwards. That's sort of my plan. So, the affiliations around the first slide. So yeah, I've joined FSI UCF technically in December. Well, there's always sort of a great transition area. I noticed Also, I've been part of the EPJ here on the bottom left, the European Pulsar Timing Array. I'll explain what that is in a moment. I've been a member of that for more than a decade. I'm a bit of an imposter putting the nanograph symbol on there, but I know everyone knows nanograph, so I thought I have to put it on there. And technically, I've been a member since last week, so that's okay. And the International Pulsar Timing Array, Daka mentioned briefly in his introduction. I'll tell you much more about that later on. That's sort of combination of these two plus a bit more. Right, so that's basically what I just said. I'll talk about pulsars, I'll talk about pulsar timing arrays, tell you where we are, complementary signs, and this word often gets spelled wrongly, but this it really is with an I. It's for free. You don't need to apply for telescope time or anything. You just do this science for free. That's great. You just need, person power to do it. And then I'll briefly summarize the things that I want you to remember because, some people fall asleep during talks. And I tend to yell quite loudly, which keeps some people awake, but not everyone. So in case you happen to doze off, the main takeaways are at the end. Don't worry. So first of all, pulsars. Let me just make sure that this thing, it does not loop. Stop this one. Make it loop. Okay, that makes more sense because pulsars don't rotate once and then stop. Pulsars actually loop. So this is a neutron star. It's an animation you don't see very often. It comes from Swinburne University of Technology in Australia, but it hasn't been very widely advertised. The reason I keep using this one, even though it's old, is because it's actually a really good representation of what a pulsar looks like. The pulsar is basically invisible. That's the basic thing you want to know. The pulsar is, as I think you all know, it's a neutron star. That means it's the collapsed core of a massive star at the end of the massive star's life. That means there's no nuclear fusion. Therefore, there's no radiation. However, it has these green lines, which are also invisible in reality, but those indicate the magnetic field. And it's got such a strong magnetic field that you get some kind of particle acceleration particularly close to the magnetic poles, and that particle acceleration leads to emission. Primarily radio emission, but basically it emits across the entire electromagnetic spectrum. Now, the next thing you need to notice is that the spin axis and the magnetic axis do not coincide. That's not crazy. That's the same for the Earth. That's also true. So for neutron stars, that's also typically the case. And because the emission comes from the magnetic poles, and you have that offset between the axes, you get that emission being swept around the space continuously. So you have these two beams of radiation that just keep getting swept around in space, and every time a beam intersects our line of sight. Yes.
So the particles are accelerated towards, right? They're caught.
Yeah, that's right.
And then they're accelerating, and then them crushing or going towards the thing creates the emission. Okay.
That's right.
Okay. Thank you.
As far as we understand. Because as I mentioned, I don't know anything about pulsars. This is a hand-wavy, sketchy kind of explanation of why we see emission. And the most important thing is why we see this emission pulsing effectively. We see pulses of radiation, even though the emission is actually continuous. That's because of the so-called lighthouse model, because this is effectively a lighthouse, just sweeps the beam around. Exactly why or how this emission works, we don't actually know. What I just told you is sort of the best guess we have, but there's lots of issues with that explanation, actually. And there's a whole heap of pulsars, and there's always some that go against whatever explanation you want to come up with. So it's a lot more complex than what I'm saying, but that's okay because we can still use them as tools. It's a bit like using a stopwatch to measure time. Even if you haven't got a clue how the stopwatch works, you can still measure time pretty well. So that's the emission. If we actually want to know a bit more about the object, the pulsar, the neutron star itself, and what kinds of neutron stars there are, we tend to look at this diagram. This is called the PP dot diagram because it's got the pulse period P on the x-axis, P dot, which is the time derivative of the period, on the y-axis. And it's often justifiably called the Hertzsprung-Russell diagram of pulsar astronomy. Even though there's no colors and no magnitudes, it still illustrates the life cycle of pulsars, really. Because what happens when a pulsar, when a massive star goes supernova and its core collapses and you create that neutron star, it starts off with spin periods, which is sort of in the middle top of the diagram, sort of around here, with spin periods on the order of a few tens of milliseconds and derivatives on the order of 10 to the minus 12 of seconds per second. That's where the young pulsars are supposed to be, the ones that have just gone supernovas, just as in hundreds to thousands of years ago. But you can see these dashed lines sort of slanting over the diagram. Those indicate the ages of pulsars, because as they age, they move diagonally towards this main island. That means 10,000 years to sort of here. This pulsar here at the top, I suspect is that one. That must be the crab pulsar, because the crab, as some of you might know, we actually have the supernova observed. Back in 1054, the Chinese kept very detailed notes about a new star appeared in the sky, supernova, which turned out to be the birth of the crab pulsar. And so for that one, we know the age very well. The Vela pulsar is also somewhere in that area. Again, the pulsar is associated with the supernova remnant. Again, we can estimate the age very well. And so it's very clear that the young pulsars are in this area. Now, the other slanted lines, dotted lines here that go diagonally down, those are the magnetic field strengths of the magnetic field of the neutron stars. And they tend to be roughly constant as these things age and as they spin down. So these things move gradually down to the right. Of course, as they move down, the spin period also decreases. That means they move slower and slower as you go. And that's why you get a bit of a traffic jam effect and why things heap up here in this main island. Yes?
Quick curiosity. Does the model for when the crab, or the age of the crab star, or whenever it was formed, or whenever it went supernova, does it match, did it match the models of what was already predicted?
That's a good question. The problem is the theory that comes up with these dashed lines here. We typically make the simplification that the pulsar started with a spin period of 0, which is not true. But for most of these pulsars, it doesn't matter. For the crab, that doesn't actually work out because it's so young. That these assumptions typically don't work. However, for the crab, we've got a number of estimates, and they are all pretty much in agreement. It's not just a historic record because they didn't have milli-arc-second precision in the days, but it's pretty clear that it's from that time. Things are pretty consistent there. Right. So the traffic jam effect, which causes the main island. This main island, that's what we call the slow pulsars. They have spin periods on the order of a second, give or take a factor of a few. That's not actually where they end because they keep moving and eventually they cross this dot dashed line that slants here. That's called the death line. You can make all sorts of funny names in this kind of story if you like. When they cross the death line, they get into the graveyard, and there's a few zombies here that stay alive, stay emitting in the graveyard. Mostly in this region, there must be a huge number of neutron stars. It's just you can't see them because the spin down has become so slow, the spin itself has become so slow that there's not really enough to drive the emission mechanism. I remind you, we don't actually know how the emission mechanism works in the first place, but we do know that they turn off. And there's actually clear evidence that in this region, sort of pulsars become very flaky, they start flickering like a light bulb that's about to die. So there's a bunch of pulsars here, slow pulsars here. What are all these here? They're circles, not dots. The reason for that is these are in binary systems. And if you have a neutron star that is in binary system with preferably a star that is a bit lower mass, then sooner or later that star the companion star is going to grow into a red giant stage, at which point its outer layers are going to get so close to the neutron star that it's going to accrete matter. For that, you might say you need a tight orbit, but then if you didn't have a tight orbit, the binary would have probably been broken up when the pulsar went supernova anyway, and that's why all of these are single. So, when your neutron star in its relatively tight binary accretes matter from the companion star, it also accretes angular momentum. That means these dead pulsars in the graveyard get spun up, get recycled into these circles here on the bottom left. And so that's why these extremely rapidly spinning pulsars, so-called millisecond pulsars, why they have high spin period, why they are basically all in binary systems, and why they have such a much weaker magnetic field, because in the process of the accretion, the magnetic field also gets somewhat weakened. So that's the millisecond pulsars. The nice thing about those is, well, there's a whole bunch of nice things about those. That's why I'll basically be talking about these the rest of my talk. They're extremely rapid rotators. They go down to the millisecond level. That's why we call them millisecond pulsars. That also means that if you want to measure the arrival time of a pulse, these are much more precise than the slow ones. It also turns out they're a lot more stable than the slow ones. Whatever happens here internally can cause the pulsar to behave in a weird and unpredictable way, which I'll spend a lot of time talking about because it turns out that's a real problem for gravitational wave detection. These also do that, but not anywhere near at the same level, at a much, much lower level. So they're much more stable. That means as a clock, they're much nicer to use. These are in the middle, that's another population. They've also been recycled, but they haven't been recycled quite as much. They've accreted angular momentum, but only a fraction of what the MSPs recycled, accreted. And so these tend to be systems, well, neutron stars that were orbited by a more massive star. As you probably all know, more massive stars go through their phases of stellar revolution more quickly. That means they're red giants for shorter than these companions, and therefore there's less accretion. The consequence of that is that here you have binary systems with two massive stars, a neutron star and a companion that also typically turns into a neutron star. So this is the area where you find the double neutron star systems, which is really nice for tests of relativity, but for gravitational wave detection, they're sometimes useful. It depends a bit on the system, given that they do rotate more slowly. Right, just to sum that up, I've skipped over the magnetars. There's only a tiny group of those. They are not all detectable in the radio. Mostly they're observed in X-rays. And because there's so few of them, they're not really that well understood either. The thing that sets them apart is they have much stronger magnetic fields. They're extremely unstable. Their spin period is not really predictable at all. And so there's lots of open questions there still. So what we want to do now is take these MSPs here and time these and see what we can do. Now, how does timing work? It's basically quite simple. It's like basically any modeling effort in physics or science. You have an observation, and here on the top you can see the observed pulse train, whole series of pulses that come one after the other. You can, of course, have a model that predicts when the next pulse should arrive. The most basic model would say, I know the period of the pulsar, therefore I know every so many seconds I expect the pulse. You can make that a lot more complex, but fundamentally you predict when the pulses arrive, and then you just take the difference. You check what the difference is between the observed arrival time and the predicted, and that is what you call your residual. So that mathematically, if you like, that's sort of written down here on the left in a simplistic way. Observation minus model is residual. That's not just the pulsar time, that's very general. Give you an impression of how that goes, like how that modeling goes. In principle, I've written down this here on the bottom. It glosses over the details a bit, but it gives you the idea of the kind of terms that are involved. There's of course the pulse period, in this case nu for frequency, but you know, that's a matter of taste. Nu dot, which is then the period derivative. Time, of course, because these can all depend on time, and so that term basically determines the phase of the pulsar's rotation at any given point in time. This term here illustrates the propagation delays through the interstellar medium, because free electrons and parts of the interstellar medium are ionized. The free electrons affect the group velocity of light. That's a frequency-dependent effect, and therefore you get a frequency-dependent travel delay through interstellar space. That needs to be corrected if you want to know when your pulses are going to arrive. R and S are vectors that determine the positions of the Earth and the pulsar with respect to the solar system barycenter. That means this term and that term, they basically include effects like the position of the pulsar. The proper motion is here given here in the VT term. The parallax plays a role in that as well, because depending on how close the pulsar is, the curvature of the wavefront changes, and so that has an impact on when your pulses arrive as well. There's a whole bunch of terms that I've left out. Those are mostly terms to do with binary models. Because if your pulsar is in a binary system, and you measure these arrival times of the pulses to a precision of a few nanoseconds or tens of nanoseconds, then you need to know the orbit extremely well. And so in practice, there's orbits that we know the size of down to the millimeters level. So it's extremely precise. But that does mean that the mathematical description needs to be extremely accurate as well. And so apart from the standard Keplerian orbital models, you tend to have post-Newtonian relativistic terms in there as well, which are needed to make sure that the observations and the model match. Yes?
Since the amplitudes in that observed terrain are not constant, I would think that introduces some ambiguity in the arrival time. Do you have a way to handle that?
We do, and that's an excellent question. That actually jumps a bit ahead of what I was gonna say, but I can skip that slide as well.
Wait, I can wait.
No, that's all right. Let's take the questions. What I just told you about the timing, you take observation, you take model, you subtract, you get residual. That's sort of the dummy's guide to starting to think about this. In practice, this diagram tells you in a bit more detail how we do this, because you pointed out correctly, the amplitude of the pulses changes. In fact, what I didn't tell you, but it showed in the animation earlier, the shape of the pulses also change. So pulses can sort of move around a little bit. It's what we call pulse phase jitter. And it's really problematic because if you have a pulse with a period of a millisecond and the pulse moves around by hundreds of microseconds, you're not going to do nanosecond precision timing. However, it turns out, and this sketch sort of tries to illustrate that, when you have one pulse coming, and so this is the frequency dependent delay that I was just talking about, what you can do is you can take multiple, well, a series of pulses, and because you know the pulse period to first order, you can fold them all together. So you average down the noise, but you also average down those variations, those single pulse variations. And the funny thing is, and that's one of the really problematic questions about the pulsar emission mechanism, if you compare one pulse to the next, they always asterisk, there is never an always in pulsar astronomy, there's always exceptions. There's always going to be differences between adjacent pulses. However, if you average 100 or 1,000 pulses together, and remember, for a millisecond pulsar, you only need a few seconds to get 100 pulses, it's going to be incredibly stable. The amplitude is going to be mostly stable. The shape is going to be perfectly reproducible. And if you do that next week again, it's going to be identical. And so at that point, you can actually, you have a stable, what we call pulse profile, others might want to call it the light curve. It's stable, it's reproducible, therefore you can actually use that for some cross-correlation techniques, which can get you a very precise measurement of the arrival time. Right? So yeah, there's a lot that I'm sweeping under the carpet because this is not an advanced graduate course in pulsar timing, it's sort of an overview of how we do things. But do keep asking, because it's good to highlight these things. But so anyway, when we do this and we have, this very simple idea of comparing the model to the data, what that ends up looking is something like this, where you have the residual on the y-axis, time on the x-axis, and this is a data set. It's sort of not a poster child, let's be fair. It's a very bog standard pulsar. In fact, it's a very nice pulsar. It's got a half-year orbit, which means that it's really hard to get the orbit right for this one, but that's a technicality that you don't need to know. Anyway, it's got a timing precision of about 1.1 microsecond. That means that the root mean square of the residuals over these, 20 odd years, almost 30, is about 1.1 microsecond. Individual measurements can be a lot more precise. They vary a lot, and that is partly because of interstellar scintillation, which is, again, something that's going to change the amplitudes. But if the amplitudes change and the shape doesn't change, then you can still measure the arrival time. So, first thing that you might notice, and I say might because that might not be obvious to everyone, but there's a lot of different things combined here. Here in the legend, in the key, you can see all of the different types of data that go into this. The data are sort of split up based on telescopes. So these three colors are Effelsberg, then there's a couple from Bank, there's some Nancy from France, there's some Westerbork from the Netherlands. And within each observatory, you still have divisions based on the observing frequency, based on the data recorder that was used. I mean, over 30 years at a radio observatory, well, at any observatory, a lot changes. The instrumentation does get changed because technology improves. So as you get new data sets, new instruments, new receivers, the data properties change. And if you want to analyze the data set, you can't just assume that everything has the same properties. You need to differentiate between those. So that's why you get this very inhomogeneous combination of data. You can also see that around 2005, suddenly, not only do you get more colors, so more telescopes are observing, there's more points, there's more intense observations, and that sort of keeps getting more and more intense as we keep going. But also the scatter becomes larger. That's partly also because we divide up our data in a different way to get more data points rather than average data points that are very small. So, technical reasons for that, but the point is this whole thing is intensifying, and mostly what you see is white Gaussian noise. Yes?
Is there no way to keep track of how much time has passed if you're not constantly looking at it?
Yes, that's again a very good question. What you do is you need to tag your data very precisely to the observatory clock, which is itself tied to GPS most likely, and so you have an international timestamp at which you connect these things to. This is something that sounds straightforward. In practice, that's something that often goes wrong. Right, so that's what I was leading up to. The reason I included this figure was not to explain folding. I wasn't really going to go there. It's just to show that the idea of taking observation, measuring the peak and sort of comparing to the peak of your prediction is in reality very much simplified, and there are many more steps involved, all of which can introduce errors and problems. And that is sort of the bottom line when the question is, did we detect gravitational waves? Well, there's so much going on that we need to make a lot of things short, and that's what's making this whole business fairly slow and cumbersome. But anyway, importantly, everything we know, everything we can model, everything we can describe mathematically is included in the timing formula. Everything that actually happens in real life is included in the observations. That's the nature of observations. If it's not in the observations, we can throw it out. That means that everything that happens in real and that we have not modeled is in the residuals, and that makes the residuals so valuable because they include all the new knowledge. That also means the residuals do contain our gravitational waves, even if we haven't detected them yet. Now, what is in those residuals? What exactly do we expect there? Well, there's a whole bunch of things. The most important ones are listed here. There's, of course, Gaussian measurement error. I pointed it out already. You cannot get away from that. Just white radiometer noise. There's the erratic behavior, which I call timing noise. I mentioned that briefly earlier. Slow pulsars have a lot of timing noise, all of them. Millisecond pulsars don't, or at least they have it at a much lower level. But they probably do as well. We just don't know at what level yet. So anyway, that's variations, random variations in the residuals. Gravitational waves, if you believe they exist, and we know they exist, is just the type that we're looking for. Well, if they exist, they're there. There may be other things as well, and I'll come back to a few of those in a moment. Now, the thing is, when you have all your residuals, what you need to do is figure out every deviation I see, what is it caused by? What is it due to? The way to do that is by looking at the signatures of the various potential effects that you're looking at. And then there's two possible ways to go about that, to discriminate between different signals. There's looking at the spectral properties, or in fact, the signatures in either the time or the spectral domain, just to see how a particular effect would impact your data. And correlations, where you don't just look at one pulsar, but you look at a bunch of pulsars and see where there's a common signal. So spectral properties are just plain direct impact of a signal on a given data set. That's basically what we see for most timing signals. You can imagine an orbital period would have, for example, a sine wave introduced into the timing residual. That means if you have the orbital period, or in fact, in the case of this figure, if you have the position of the pulsar wrong, your predictions will be off by an amount that changes sinusoidally. So if you see, in this case, in the time domain, that there's a particular signal, you can see, look at that in the spectral domain, you see a single spike, then you know what kind of parameter you have wrong in your timing model, or what kind of parameter you're missing. So I did this plot again. I won't go into detail. It comes from a handbook chapter that was published just last year. Well, it sort of took a while to get out, so I guess it actually came out last year. Anyone who's interested in a bit more details on the practicalities of pulsar timing, you can go and look there. It's got plenty of references for further reading as well if you want to. But so yeah, a lot of things like position, orbital period, etc., have very clear signatures which allow you to directly measure them within a given data set. The problem are the things, the effects that are stochastic. Those are, for example, gravitational waves. If it's a combination of many gravitational waves, we talk about a background, and at that point, the timing signal is not so clear anymore. It's not just a simple sine wave, it's a stochastic random superposition of signals, and then you can't really model it so deterministically anymore. If it's not deterministic in the time domain, often it is somewhat deterministic in the spectral domain, and the gravitational wave background is one example where we do roughly know what kind of spectrum we expect. So what if you take the Fourier transform of the timing residuals, how that should look. The reason we know that is because we think we have reasonable understanding of how the universe evolved. That's not a joke. Some people actually believe this. Anyway, and based on that, you can make predictions. This is a plot. It's a bit outdated, but it gives the ideas and the concepts behind these predictions very well. That's why I keep showing it from Alberto Sassana in Milan, or it probably was in Birmingham when he made this. It shows you the strain of the gravitational waves against the observing frequency. Sorry, against the gravitational wave frequency. And so what he did was he took the Millennium Run, which is this huge simulation of the universe. He identified galaxy mergers. In those galaxy mergers, to these galaxy mergers, he assigned supermassive black hole binaries, which he gave some parameters based on the size, etc., of the galaxies involved. And then each supermassive black hole binary, of course, creates a gravitational wave sine wave, just a monochromatic wave. So each of those binaries is one of these green points here. So they have a very well-determined frequency, which is determined by the orbital motion of the black holes, called an amplitude that is determined by the distance to Earth, as well as the masses and the chirp mass of the black holes. And so for each of those supermassive black hole binaries, it's got a green point. Then in each frequency bin, he adds up those signals, and that's the red line. It shows you the amplitude of the gravitational wave signal as we would observe it in our pulsar timing data set. And so what you see very clearly, that there's a lot of sort of noise here on the right end, but those are frequencies we're not really sensitive to. It's really the lowest frequency band that we use, that we are sensitive to. What you see very clearly is that the amplitude is very strongly dependent on the observed frequency, and it's most strong at the lowest frequencies. That's what we call a red noise spectrum, because if in the optical you have something that is most powerful at the lowest frequencies, it looks red. Yes, and so that's basically the stochastic background that I was talking about. You cannot identify single sources because they've all, this single bin is a combination of all of these here. The phases are completely mangled. You cannot get a coherent signal. In the time domain, it's very random. In the frequency domain, it's a very clear, well-defined spectrum. The red triangles, they're above that red line, and those are supermassive black hole binaries that are so strong, mostly because they're so nearby, that they actually dominate the signal within their frequency band. That means you have a huge sine wave at that particular frequency, and all the other contributions are minor ripples on top of it. So that source there on top, hang on, let me show that for the remote audience as well. This one here, that would be a single source that you can actually see as a sine wave in your timing residuals, because it's so much more powerful than all the others. Now, that's all arbitrary, really. This is one realization of a universe. We don't know what our real universe looks like, and therefore we don't know if the first signal we'll see is the red line or the red triangles. It depends where the supermassive black hole binaries are. And in fact, if you had asked people 5 years ago whether we would see a single source that has a nice time signal, or whether we see a background which is just spectral domain, people would have answered you that it's probably 50-50. We don't really know, could be either. Now there's good reasons why we're all shooting for the background, because it looks like that might actually be happening sooner.
Just
Yes.
from my understanding, sorry, so these are galaxy mergers that are observed today.
Nay, these are from the
Okay.
Millennium Run.
Okay, so these are galaxy mergers that are extrapolated from today's population into the past.
No, you should ask someone who knows about the Millennium Run, but my understanding is that the Millennium Run does not really connect to today, but rather takes what we know about the early universe, and particularly how dark matter was distributed and would cluster, etc., and forward evolves that. Unless somebody knows otherwise.
But if, I don't know, you let me know. If you forward evolve it enough, do you get what we have today, like the population that is seen? Or are these all gone?
I suspect statistically, yes, but not in detail.
I see. Okay,
Because of course, I mean, it's a random
okay,
realization.
and what's happening there?
The bottom line.
Yeah.
Yeah, this is just the cutoff where he stopped plotting the green points because it's not his printer that's running out of color. It's just that the plot
Too
becomes
many. Okay,
uninformative because this is basically all filled with single sources.
I see, okay.
That's why you only plotted it down to a certain,
Mhm.
certain level of impact on the timing residuals.
But this stochastic expectation is for today.
Yes.
I mean,
But so depending on how the universe exactly, what shape and form the universe really has, depending on the distribution of supermassive black hole binaries, these red curves could jiggle around a bit.
yes.
It would go up a bit, down a bit, and etc. The thing is, once we actually detect it, then we can nail it down, and then we can actually say things about
Yeah,
galaxy
yeah,
mergers and say this is how it was, and this is definitely how it not, was not.
Okay, but it's supposed to be a prediction, sort of.
Exactly.
Mhm,
Exactly.
mhm. We can proceed.
Yeah, I don't like talking about cosmology, but if I'm forced to, well. So it's a red noise spectrum. That means in the time domain, it's unpredictable what it will look like. In the spectral domain, it will look like something that has most power at low frequencies. Now, what does that look like in the time domain? For example, like this. This is a red noise spectrum here. The spectrum is on the bottom. You see the white noise level is there at the highest frequencies. That's where the power is sort of evenly distributed. And as you go to lower frequencies, power ramps up in a somewhat random way because there's a lot of noise included as well. Of course, it's one data set, one simulated pulsar. So that actually this is not simulated, this is real data. So the power goes up to its low frequencies. The phases are all random, of course. So it could look like this, it could look like something completely different in the time domain. So that's what it looks like. Now, the problem is there are other sources of red noise, which fundamentally would look the same. Timing noise I already mentioned, right? Those fundamental instabilities and drifts, etc. Interstellar medium I have mentioned, but not in this context. I did tell you that the free electrons between us and the pulsar delay pulsar signal. Now, the interstellar medium, especially the ionized part, is highly turbulent. So it's got a lot of density variations. It moves around a bit as well, but more importantly, the pulsars move around. Pulsars typically have velocities on the order of a few hundred kilometers per second. So they move through the galaxy pretty quickly, which means that our line of sight also moves through. And that means that we actually probe different parts of the interstellar medium, different parts of this turbulent ionized component as time goes on. And that means that the delays also change in time. That's a big problem because it's very hard to correct for that. What I spent my last 10 years on, basically. So there's progress, but it's not solved yet. And it fundamentally would look like this. And the gravitational wave background, which I already said, looks exactly like this. There's also other signals that could look red, depending on their manifestation, but they're somewhat different because timing noise in the stellar medium, they're very pulsar dependent. An individual pulsar would have a different signal than another pulsar. Clock errors, if your station clock is unstable, or in fact, if the international time standard is not quite right, clock errors would also introduce potentially red noise signals. And solar system ephemeриds, the Earth is not a particularly inertial system. So we tend to measure all of these arrival times with reference to the solar system barycenter. Now that only works if you know where you are with respect to the solar system barycenter, which means it works if you know where all the bodies in the solar system are and what their masses are. And so that may go wrong sometimes. And that would also then introduce features and signals that might be similar. The nice thing, though, about clock errors and solar system ephemeриds is that these affect all pulsars in a similar way. Right. Which is true for gravitational waves as well, because what a gravitational wave does is it distorts space-time. And if space-time is distorted, you're going to see that in all pulsars because it's the same space that we're sitting, the space around the observatory in particular. The differences are then that clock signals affect all pulsars exactly the same. Your station clock is your reference time. If that drifts over time, it's going to affect all your observations in exactly the same way. So that's what we call a monopolar signal. There's a complete and perfect positive correlation between all of your data sets. Solar system ephemeris, that is to first order a dipolar error, because at any point in time, if the solar system barycenter is slightly off from where you expect it to be, then pulsars on one side of the sky are going to be delayed or appear delayed. On the other side of the sky, they're going to appear too early. And so it's basically dipolar. I say it to first order because as time goes on, of course, as Jupiter moves around the sun, this offset is going to move around as well in some kind of way. And so that dipolar signal changes in time, but that's just extra complication. Gravitational waves are dipolar, quadrupolar rather. I'll try to briefly explain that with a bit of a thought experiment based on Wikipedia. Imagine you're at the center of the universe, right here in the middle of the blackboard, the whiteboard, screen, whatever, here. And all the other things in the universe are pulsars, which is a nice universe. That's the black dots around you. And now imagine there's a gravitational wave traveling perpendicular to the screen. What that gravitational wave does is it distorts spacetime, as I said, in the plane perpendicular to the propagation velocity, so in the plane of the screen. The way it does that is by stretching and squeezing opposing sides equally. In an animated form, that would look like this. And so the left and the right hand does just two different polarizations. In reality, you'd have a combination of those. So exactly how this thing moves around is a bit unpredictable. But the important thing is the effect on the timing, if you look at the distance to the pulsars, is going to be identical or very similar for pulsars that are close together on the sky. It's also going to be very similar for pulsars that are opposing parts of the sky, but it's going to be exactly opposite for pulsars that are 90 degrees apart. That means if you want to check if there is a gravitational wave in your data, you want to make use of this so-called quadrupolar signal. That means you'll take your data set. Yes?
I don't want to interrupt. You can finish
Okay.
the sentence if you want. But
You take your data set and you cross-correlate the data, the residuals for different pulsars. Then you check how much correlation you have as a function of the angular distance between the pulsars on the sky. And that will look like that, which is the quadrupolar signal. I'll get back to that once I have your question.
But so you're in this, what you're showing, you know how we see everything 2D technically, right? But the pulsars that are in the same corner of the sky, they may not be close to each other. So now you're detecting a gravitational wave that passing through you. Is that what you're doing? Not that's passing over there.
It's passing everywhere. That's a tricky point indeed. And that's again something I tried to swipe with the carpet. The gravitational waves distort space-time everywhere because these are cosmological sources that come from redshift 2 or 3. That means they're going to affect the pulsars and space between the pulsars and Earth. However, because the gravitational waves move at the same speed as the pulsar signals, the speed of light, the distance to the pulsar doesn't actually matter because somehow the photons just travel along with the wave and nothing really matters. This is how the theorists explain it. It's a very hand-wavy way, but mathematically, I'm sure it's robust. That means the distance to the pulsar doesn't matter, but the pulsar itself, the space around the pulsar where the emission happens, that gets affected, as well as the observatory. Now, the observatory gets space-time squeezes and stretches. Remember, these are low frequency waves we're looking at. So we're talking about wavelengths of the order of 10 years or so. That means if we observe a pulsar today and a pulsar tomorrow, the impact of the gravitational wave is going to be the same. The deformation is going to be static on that kind of short time scale. And so the wave has an impact both at the pulsar and at the Earth. This is a problem because it means that effectively the correlation here, which I said would be perfect, is not perfect because it's only the Earth term, so to speak, the deformation at Earth that is perfectly correlated. The deformation at the pulsar is not, and that's why this correlation curve maxes out at 0.5. So if you had a double pulsar system, two pulsars that orbit each other, which you can both time, then you would have a spike at 1, because the local deformation would be identical to the Earth deformation between the two pulsars. The Earth deformation as well, that's always the same, because then you have a correlation of 1, otherwise you max out at 0.5. Right?
Will this quadrupolar nature, won't it get washed out because of the stochasticity of the background and the isotropy of the background?
The answer is no. But I'm having trouble thinking of an easy way to explain it. So maybe we should take that offline. It's probably related to the fact that the gravitational waves we're looking at are indeed really low frequency, and so they don't change very quickly. And therefore, within your timing set, the fact that the timing behavior is sort of random in time doesn't really affect the kind of time lags we are talking about. That's probably not a very good explanation, but that's the best I can do right here on the spot. Right, but so the critical thing, yeah, excellent, thanks. The critical thing is that you have positive correlation here at small angular separation. You have a positive correlation at large angular separation. That's in radians, which is a great unit. Large angular separation is basically opposite parts of the sky. And you have a negative correlation, sort of 90-degree angles. Yeah, and so that's the signal you're really looking for. This is a simulation, again, from the handbook kind of thing. A simulation of, I think, 20 pulsars or so in a 20 pulsars means you have about 190 pairs. And you can see there's a lot of jitter around. If we could detect this kind of signal, that would be fantastic. In reality, the signal to noise is going to be a bit less. So I need to speed up a little bit. What determines how sensitive we are? Well, this is basically the equation that's been given, that's been derived about a decade ago for our sensitivity, the signal to noise to gravitational waves. There's 5 factors in there. The amplitude of the gravitational waves we have no impact on. The things that we can sort of influence is the number of pulsars, which is the most important part of it. The length of your observing campaign. So that means you need to use all the archival data you can use really. That's also why Arecibo is still playing a big role in this. The timing precision, which means you need to be extremely precise, and that's exactly why the millisecond pulsars are useful, slow pulsars are not. And the cadence, how often you observe. Cadence is something that's very hard to obtain at a given observatory, but it's something that you can obtain if you collaborate internationally.
I have a question following it. Do you see this quadrupole nature after taking out the dipolar part because of the galaxy's motion?
I think I was getting to that, but since we're running out of time, maybe I'll just take it now. I said there's basically 3 types of correlations. There's the monopolar for the clocks, dipolar for the solar system, and the quadrupolar for the gravitational waves. A long time, people thought that's easy. We subtract the monopole, we subtract the dipole, and then we can detect the quadrupole. It turns out it's a lot more complicated because you effectively need to subtract them all at the same time, which means you actually need a lot more signal to noise than we always thought. And this is also sort of the problem we are having right now. We think we have a signal, but we need to prove that it's quadrupolar. How do we do that? By figuring out what the different contributions of the different correlations are. And that's really tricky as it turns out.
No, the dipolar part which you mentioned is because of the solar system ephemeris part. But what I'm talking about, the dipolar part, is the dipole due to the motion of the galaxy with respect to the CMB.
Oh, but that doesn't matter because this all happens within the galaxy. So the pulsars we use are all galactic. They're all in the Milky Way. We're all moving together.
Yes,
So,
but the gravitational wave is coming from outside.
but the redshift of the gravitational wave doesn't matter for us.
Doesn't matter.
It doesn't matter because it's just the local deformation at Earth that plays a role. And so if you want, I presume,
Yeah,
if you detect a gravitational wave and you will interpret it in an astrophysical sense, you'd have to take that into account, I imagine. Although, again, these gravitational waves come from redshift about 2 or 3 typically. I'm not sure how important the CMB dipole is for that. Not so good beyond redshift 0.
Okay.
But yeah, it's a good point. For the astrophysical interpretation, we're not there yet, but that's going to be a whole new can of worms. Anyway, what I wanted to point out with this slide was that many pulsars, many observations, high cadence, you can't do that with a single telescope. That's why you basically use every telescope you can get. And so there's 4 major collaborations in the world that have joined together. There's the Parkes Pulsar Timing Array, who started this whole game back in 2005. There's the European Pulsar Timing Array Nanograph in North America and Europe, which both started around the same time, around 2009, 2010. Use a whole variety of telescopes, including Arecibo. It may not be around anymore, not in the shape it used to be, but it's got a lot of archival data, and that's still extremely useful. And the Indian Pulsar Timing Array, contributing 2 telescopes, which joined the International Array just last year. All of these are now frantically trying to analyze their data to try and get, an idea of the correlations. As mentioned, we have a signal, there's something there, but to show that it actually is correlated or not, you need everything you can get. And so that's where the international collaboration really becomes important.
So all these people work together.
In principle, that's my job, to try and make them work together. That's why I'm here.
Good.
Yeah, there's a lot of politics we could talk about over here. Anyway, so they all form together the International
Well,
Pulsar
yes,
Timing Array.
because how big is this going to be once you can announce a detection?
It's a good question. Of course, LIGO already detected gravitational waves. It takes a bit of limelight away, but still, it would be a completely new thing because the source of gravitational waves is completely different, of course. Yeah, it's a good question. How big is it going to be? I don't know.
Okay,
That's something for the politicians amongst us to
well,
figure
that's
out.
why everybody wants to.
That's why everyone wants to
know.
be included, but also because this is
link it.
a signal that increases in signal to noise very gradually. if you bind this all together, you can make a jump in signal to noise. So doing it on your own, you'd have to say, wait another decade before you finally get the data you need to actually make a robust detection. In the meantime, constantly worrying that someone else is going to scoop you. If you do it all together, you might still need to wait a couple of years, but you get that boost straight away.
I agree totally. I'm just wondering.
The practical and social and human aspects to it.
Okay.
Let's focus on the science. That's much more fun. So, are we there yet? This was sort of the big thing that got everyone into a craze 3 years ago, almost 3 years ago. Nanograph effectively published back in 2020 a paper where they said, we see something. It looks like it could be gravitational waves. And you need to be very careful how you word it, because otherwise people are going to get upset that you're jumping to conclusions which you shouldn't jump to, but not again. What they found was red noise. That's good because that's what gravitational waves look like. That's bad because that's what lots of other things also look like. Critically, though, they found it's common to all the pulsars that they observed. Well, almost, give or take.
What's the journal?
Probably actually letters or so. I don't remember. I don't think it was Nature. Don't think it was Science, although it might have been.
Okay.
I think it's actually letters. Problem, though, is there's no evidence of correlations. That means we have something that ticks a number of boxes, but the critical box is not there yet. This is the result of their Bayesian analysis. This shows the probability density function, say the likelihood of a signal being in your data, as a function of gravitational wave amplitude. And what's shown here is for a common red process. That means if you tell your Bayesian code, how strong would a signal be if it's common to all the pulsars? So that's this distribution, which means it's definitely there. It does not have amplitude 0. There is a common red noise process in there. If it's a gravitational wave, that means if you tell your Bayesian code, suppose there's a signal in there that's quadrupolar correlated, what would the amplitude be? It's got a very clear upper limit, got a bit of a bump here, but it's not very significant. In fact, it's not significant at all. And then a very long tail that says it could be 0. Which means we can't say it's gravitational waves, but we can say it's something that looks like gravitational waves. And that's basically what they said. Of course, immediately the Europeans and the Australians jumped up and woke up and got working. And in the next year, they both published their own papers where they said, we see the same thing, hey, which is good, because it means that it's not just Arecibo and Greenbank that see this, it's actually probably astrophysical.
So what you're saying is you see the cross correlation between the noise, but not the expected correlation. Is that what you meant by no evidence?
What I meant by what?
Is that what you meant by no evidence for correlation? Or?
It means that if you look for correlation, you get a statistically insignificant result.
So the red noise is not correlated from pulsar to
If the
pulsar.
red noise is correlated, it's at a level that is below our sensitivity threshold.
Okay, so
That's what it means. Which means it doesn't mean anything, really. Now, it's a bit more complex because you're using Bayesian code, which most people use as a black box, with good reason. So you might want to do some simulations to figure out how your black box really works. And that's what the Europeans and the Australians also did. The Australians came out with this plot here, where they took their pulsars and they made simulations. And they said, if we inject red noise and we change the spectral index of the red noise, so the steepness, and we change the amplitude, so that for each pulsar, that's all of these crosses here, we have something that is somewhat similar, but not really the same. That means, for example, timing noise. If these pulsars have timing noise at about this level, which is just below our sensitivity threshold, therefore we can't really see it. It could be like this, for all we know. What does this very same base code tell us? Does it tell us it's a common signal, or does it tell us that no, all these pulsars have something slightly different? Well, lo and behold, they come out with sensitivity curves that are pretty much exactly like the nanograph sensitivity curves. Well, that's not really a surprise because these injected signals, they plot here as dots because it's a simulation, so you know exactly what it is. However, if you were to measure the red noise properties in any of these pulsars, the uncertainties are going to be bigger than that. That means for this pulsar, your uncertainties would be quite broad, and therefore everything could be consistent with a common signal, common spectrum. So they basically put up a caveat. They said, we see the same common red noise signal. However, given the properties of our data, the Bayesian software may be misunderstanding what we mean with common. It may actually just say, given the uncertainties, a common spectrum is a reasonable assumption, and you need to be careful there. Europeans did a somewhat different thing. We looked at measurements that were outliers. So you saw the timing residuals, they all look nice and white. Now, sometimes there's a few points that are off for good reasons, for example, because of the solar wind influence. And it turned out, as far as we could tell, if you have a few of those outlier points, which you haven't removed because there's nothing wrong with them, they're just not where they're supposed to be, then your code could also mistake that and say, oh, your uncertainties are underestimated. There's actually a lot of noise there. And it could also find red noise where there isn't necessarily any, or rather where the actual problem is different from what you expect it to be. That goes back to the basis of Bayesian analysis. Bayesian analysis tests whether a model can describe the data, but if your model is flawed to begin with, you're not going to get an accurate answer out. And so, again, there's a number of caveats that claim that this is analysis you need to be very careful with. Anyway, let's forge on. So each PTA independently went around and checked, and they all found basically the exact same signal. They all found that it was common, given the caveats we just went through. There's a spectral plot just, to show the red noise spectrum and see how, complementary the different PTAs are. And now what we need to do is find the red noise, the correlation between pulsars. In fact, so we need to look for the correlation, and that's exactly what's happening now. All the PTAs have been looking for that independently. Right now, as we speak, they're all writing their own paper to describe what they found. We'll orchestrate the publications so that you can see from all the PTAs what they found. So I'm not allowed to disclose what's in there yet. Yes?
In that red, can you go?
Yeah, sure. Hang on. Yeah.
So if I understood that plot correctly, that is the spectrum of the red noise.
That's right.
Now,
Well, that's the spectrum of
the
residuals, effectively, yeah.
Essentially. So in the spectrum of the residuals, there should be a red noise because of your clock errors. How did you take that out?
I was about to get to that.
Okay.
Yeah, so there's multiple types of red noise that could be in here. And that's why this plot doesn't actually show you anything about the correlation, it just shows you what the spectrum looks like and what source that has. And there's a different question. That's right.
And what you're saying is this noise, this red noise, although it shows this slope for different pulsars, they are not correlated.
That's exactly what we're trying to figure out now.
Okay.
So whether it is or not, I cannot really disclose to you yet. That will come out in publication, and hopefully in the next few months or half a year or so. But at the time that they published this, like in the last couple of years, then it was not correlated as far as we could tell. That's right.
Okay.
All right. Yes, so that means right now we're looking for the correlation. Now, I can't give you a spoiler on this, as I already said. But you can imagine if 2 years ago there was no significant correlation, even if there is one now, it's likely to be fairly faint. So it's not going to be Six Sigma detection in 2 years. However, once you put all the PTAs together in the global IPTA, in fact, now we've got Indians as well contributing. So it's progressing quite a lot. Maybe then within a year or so, we do get something that's actually significant. But, we will need to wait and see. Now, meanwhile, there's a number of things we can do. And the first one I was going to point out was the clocks. This just happened again 2 years ago. This is a study, Hobbs et al. 2020, which you can look at, where they used the globally combined data from the time to look for monopolar signals. And so what they did, there's several realizations of the global time standard. TAI is sort of the most basic one, and then BIPM is where they take TAI and after the fact figure out what was wrong with it and correct it. And so BIPM is basically the best time standard we have. On the vertical axis is the offset, so the mistake in the clock, basically. On the x-axis, it's time. So again, from the mid-90s to, well, somewhere in the early 2010s, because that's when this particular data set ended. BIPM is the best time standard we have, so they just check, if we just look at our pulsars and compare the monopolar signal we get to BIPM, what does it look like? The red line is what you'd expect, because BIPM is supposed to be perfect. The measurement points here and the blue the regions, that's what we got out of the measurements from the pulsars. So you see, it's actually very consistent. It's very accurate. This here shows the residuals, so the difference between the two, which in this case, of course, is 0 because the model you're subtracting is 0. And in fact, in the mid-90s, there's some deviations, some problems there, which are probably to do with a few of the Parkes data sets, which, well, these were early days, so we didn't have a lot of data yet. But in the recent times, actually, things are very consistent, and it doesn't look like the BIPM model is actually significantly wrong. It doesn't look like that's causing a problem. Of course, that doesn't mean that we're not looking for a monopolar signal still. Maybe something did go wrong, but it doesn't look like it. TAI, again, TAI did have some variations because we know TAI has issues. That's why there's BIPM ultimately. And you can see we can reproduce that signal pretty well, actually. And then this was just a simulation where they introduced the signal. And again, it looks basically like the method works, and we can actually dig that out reasonably well, though not perfectly. So there's ongoing work for the monopole. There was also ongoing work for the dipole. This is 2018. It uses the same data set as before, but this time it looks at the solar system ephemeris to try and see how sensitive are we to the masses or errors in the masses of different solar system bodies. And in fact, it's not just bodies, it's systems. Because of course, when we say Jupiter, what we are sensitive to is the total mass of the Jovian system, including all of its moons, which is kind of unique. Anyway, this was the sensitivity at the time. So these stars are the IAU official values of the masses of the different planets. These curves show our sensitivity to bodies of a certain mass at that particular distance. These green dots, I think, are our sensitivity to a change in the mass of this particular body. That means at that point we have the phase locked in already. We don't need to fit for the phase. That's why there's a bit of the increased sensitivity there. Then the yellow triangles were the IAU uncertainties at the time. Now this one has significantly improved since. That's we need to get the publication out before they have updated their numbers. So we're not actually close to what the IAU and JPL have, but it's still nice sensitivity.
How much do small bodies, main belt and Kuiper belt, and further out affect the ephemeris?
Kuiper belt wouldn't affect it much because you can see our sensitivity goes up very significantly there. Asteroid belt, not sure, it might sort of average out anyway.
I mean, this effort to detect Planet 9 is based on looking at residuals in the ephemeris. How do you say that?
Ephemeris.
Ephemeris. Yeah, so that's looking for residuals to try to explain a portion of the error based on undetected bodies that are out there. So I'm just wondering, is that a significant source of possible error?
Probably not. This is based on the correlation. There's actually alternative methods you can use for specific pulsar systems to try and get limits on the acceleration towards any given direction. And so that way you can put limits on the mass of planet X that are well below Jupiter mass. So this is not the best we can do in terms of limiting planet 9 or whatever you call it, planet X. But it is the sensitivity we have to solar system errors from bodies we already know. Right. Yes.
You said that you calculated on based on the entire system, per se, like the Jupiter.
You don't calculate it, but it gets affected by the entire system.
But does it get affected, or at least the model you guys do, does it get affected by individual bodies, or is it given by the entire?
The thing we're sensitive to is the location of the solar system barycenter. So every body would slightly move that center around, and in that sense, we're sensitive. Now, when I say the Jovian system, it means that Jovian system you can consider as a point mass basically, and that's then what we're sensitive to. Ultimately, the position of that is pretty well known because that's ultimately the position of Jupiter. All right. Good. Now, I'm way over time, and in fact, I think the question time has already run out. So I'll just highlight. At low frequencies, and I work at low fi, that's sort of against the ionospheric cutoff, almost 10 to 200 megahertz. You can do these studies of the interstellar medium at great detail, and you can see what red noise looks like and what kind of crazy things happen in the turbulent medium at precisions never seen before. The same you can use to study the solar wind, because that's also an ionized plasma, and so we can measure the integrated electron density of the solar wind really well, which has shown us that the solar wind models we've been using to correct our data are completely wrong. And that's one of the reasons for those outliers I mentioned. We can also study the ionosphere, particularly with low frequency data. And so we've been comparing ionospheric density models, Earth-winged field models, etc. And we're actually quite sensitive to that.
So that would be a problem you wouldn't have if you were measuring from space, right?
That's right.
Okay.
But then the cost goes up dramatically, and that's already an issue. So.
Just
True. Putting low power on the moon would be great. No, LWH. Am I supposed to say LWH here?
what?
Never mind.
No, they're talking about it.
Masses. Pulsar astronomy is unique in astrophysics in the sense that we get both masses and distances with insane precision. Well, for certain systems, not for everything. And so as you time your binary systems, sooner or later, you're going to get relativistic effects. And therefore, you're going to get masses, sometimes with vanishing with small error bars, which is nice also for binary system studies, binary evolution studies. When you talk about masses, you can talk about equations of state for nuclear dense matter. And so that's what this plot shows, particularly really massive pulsars tend to rule out whole families of equations of state, which is something, again, that just comes out from the analysis by accident. I think both of these are PTA sources. So you time them for the gravitational waves, and you get the constraints on the equation of state for free. More general tests of relativity. This is a plot. I took the plot from 2006. There's been an update in 2021, but I thought this one looked nicer because of the yellow. So I kept it as it is. The difference is, I mean, the mass range that is allowed is so tiny, it doesn't really matter if you see the new version or not. Anyway, it's even smaller now. So once you measure multiple relativistic effects, you can check whether GR is internally consistent. And we can do that again, pretty much for free. Right, there's a couple other things that I could mention, but we're already over time. So let's just move on to very briefly summarize. And so everyone's now breathing deeply, waking up, opening their eyes and saying, aha, we learned that pulsar timing arrays can and quite possibly will detect gravitational waves. It could be very soon, but trying to do it right now. And if we're lucky, maybe what we see is indeed quadrupolar correlated. And then we'll tell you before the end of the year. Global collaboration is key. That's, again, why I'm here as the IPTA manager, because we need to work out a way to work together across time zones and cultures and whatever in order to share the data, because that's going to give a boost in sensitivity. That's going to clearly get us over that threshold if the signal is real. And there's a lot of other stuff that can be done with these data. I'm not just studying pulsars, as I said at the beginning. What I'm studying is pretty much everything else. And again, I'm very happy, very eager to talk to people and see what we can do, how we can collaborate. So yeah, come to me. I'm typically in my office. I try not to work from home too much. And I look forward to it. Thank you.
So-
I'm sorry, I'll give you opportunity to ask questions. So because we're out of time and we had the opportunity to ask questions, so I'll give priority to the online viewers. Online viewers, please unmute yourself or type in your questions if you have any. No, we have.
Maybe you after all.
Yeah,
Somebody's typing.
yeah. Okay, Phil, yeah, you can go ahead.
So, apologies if I'm gonna make a major mistake in this question, but if I understood, you're looking for correlations across the sky that have a quadruple nature, because you're looking for gravitational waves passing through our solar system. Is it possible to look at the timing of just one pulsar and see gravitational waves passing through its location?
Yes, but you would not be able to tell whether it's a gravitational wave or not.
Okay.
It's like you have a bag and somebody tells you there could be watermelons in it, there could be apples, it could be a mix of both. Tell me how many watermelons are in there. You cannot do it. Well, if there's only one watermelon, you could probably tell from the shape, but if it's a mix, you're not going to be able to do. You can put an upper limit. You can say the bag is this small, there's no way you can fit 10 watermelons, but you can never actually get a measurement. You can never detect this is definitely the number. It's the same with one pulsar. You can put an upper limit on the strength of the gravitational waves, but you cannot accurately measure how many there are.
But there wouldn't be any characteristic variation in the timing of the pulsar.
It's just random. In fact, it would look exactly Yeah, it will look exactly like these kind of things. Some very low, slowly varying red noise, which is going to look the same. Well, I say it's going to look the same for the ISM as for gravitational waves, as for timing noise for that matter. In reality, the spectrum would be somewhat different, but at the same time, where did we have that? Yeah, at the same time, you notice the uncertainties in your spectrum, they're huge, especially at the lower frequencies. You cannot really get very precise measurements of the low frequencies because for each data set, you only have one sample of the lowest frequency. The small number of statistics kill you there. And that's really the challenge with this low frequency stuff.
Thank you.
No problem.
I think I have one. So what is the frequency of the gravitational waves that are passing through?
It's a continuous spectrum. The frequencies that we're most sensitive to are on the low frequency end, determined by the baseline of our timing. That means if we've been timing for say 20 years, then the lowest frequency we are sensitive to is roughly 1/20 years. It's not quite, but it's in that area. At the high frequency end, in fact, the expert in that is also at FSI, is Ben Pereira. At the high frequency end, the highest frequency gravitational waves that we're sensitive to are determined by the cadence of the observation. So roughly 1/the cadence order of magnitude. That's the highest frequencies that we're sensitive to. So that's the frequency range that we can measure. The gravitational waves, however, they're continuous.
Okay.
We're over time.
Sorry about that.
No, it's very nice. Welcome to FSI.
Thanks.
All right, let's thank our speaker again.